Okay, so I'll talk about the general molecular dynamics algorithm and then parallelization approaches. Okay, so molecular dynamics is based on a potential energy function, which includes two terms, bonded terms and non-bonded terms. Right now, I'm dealing just with the sort of bonded terms, and what that means is that it deals with atoms that are connected together covalently. So for example, the bonds term reflects some energy due to a displacement of between two atoms, which are a certain distance apart. There's an equilibrium distance that they like to stay with at. And if they vary from that distance, the potential increases as a squared of that separation distance. The angles term represents basically the deviation from an equilibrium angle between three atoms. So if you imagine these three nodes as three atoms, if this angle varies away from a certain equilibrium theta or angle, then the potential energy is also a quadratic term, which tends to bring the three atoms to have a certain equilibrium angle. And then finally, the dihedral and improper term is probably one of the more complicated ones. The improper term basically deals with four atoms. So if you imagine this is 1, 2, 3, and 4, these three atoms, if you put two planes through them, the angle that those two planes make to each other is given a certain equilibrium angle again. And this is also, this should also be a quadratic term, but the energy also varies quadratically as that angle is deviated from. And an actual dihedral is the rotation along a bond between the two central atoms. And this energy term has actually a cosine form. So as you rotate along this bond, say for example, the energy will vary sinusoidally. And there will be a restoring potential that will tend to make it, either align or sometimes it will make the atoms stagger. So these are all of these parameters are very sort of molecule and atom dependent, and all of these parameters are available or have been built over many years by different methods like ab initio calculations or experimental calculations. But basically, if you plug those parameters in, for example, here K represents the spring constant, right? Because these are basically just like spring constraints, more or less. Or in this case, it will tell you how far up the potential will, like what this value will be at the maximum. And will, for example, in this case, will specify how many fluctuations you have in the energy function. And the other parameters are usually the theta, the equilibrium theta, or the equilibrium bond length. So this is kind of what you can expect for it to look like as molecules will tend to move. Okay, the non-bonded terms include van der Waals terms and electrostatic terms. So van der Waals forces occur between any two atoms, and if they're far enough apart, they will attract to each other, according to this formula. And if they're too close together, so at the equilibrium distance between them, the energy is a minimum. But as they get any closer, there will be a very strong repulsive force, which is the r to the 12th term. And as they get further apart, there's an attraction force, which varies as r to the 6th. And then the electrostatic force is just a simple Coulombic form. So you basically take two atoms that are, say, oppositely charged, will attract each other. If they're positively charged, they will repel each other. And it's just a matter of multiplying the charges and then dividing by r to get the energy. Okay, so to do molecular dynamics, basically, you have to take derivatives of all those formulas I just showed you. And that basically equates to the force, right? The typical Newtonian model. And that gives you the force in every atom. And then using that force, an integration scheme, this is the leapfrog-Verlet integration scheme, just gives you the velocity at the next time, well, at the next half time step. And then using that velocity at the half time step, the positions of each atom is updated. based on the positions at the previous time step and then some value. So I will show you a little bit of what it looks like on a simple molecule first. So here's a sort of simple molecule, and it has just an initial configuration that is just sort of random. That's better. And so if I just take so one technique that is done is first the geometry is minimized, which means that you just take small steps in the direction of the gradient until you reach the energy minimum. And if I do that, I sort of reach the minimum configuration that this molecule likes to be in. And then if I add some thermal noise, which means that I just set the initial velocities of the atoms to some random value based on the temperature, then the molecule starts sort of jiggling around. And the nice thing about the Verlet integration scheme is that it's actually just right, like the energy is conserved in the system, although it fluctuates a little bit. So a lot of integration schemes, the energy tends to either decrease or increase, so the system explodes. But this integration scheme is very stable. One thing that you saw there is, okay, so I just talked briefly about kinetic energy. This is kind of how the initial velocities are set based on the Boltzmann constant and the temperature. And the other thing that molecular dynamics usually do is called Langevin Dynamics. And in this case, some random velocity vector is added to the normal velocity, which just simulates collisions with other molecules in the environment. So this makes the simulation look a bit more realistic. So instead of the molecule just sitting there in space, this random sort of factor adds some movement. And there's also a damping constant, which sort of opposes the velocity by some constant. So if you didn't add any more sort of randomness into the system would just eventually go to be completely still. So there would be no more movement, because this is kind of like a damping sort of factor. And there are some properties of this random vector that sort of make some physical sense. For example, it's independent of previously picked random vectors, and it also depends on the temperature, so that if you keep adding this random factor to the simulation, the temperature will always stay constant. Another thing to consider is that these molecules, if you try to think of them as they are in a sort of typical biological system, is that they'll be solvated in water. So in that case, the Coulombic term is not actually that simple. You have to include some sort of dielectric constant. So, for example, one that is typically used, and is pretty simple, is that the constant is just the distance. So that makes the electrostatic energy dependent on 1 over r squared rather than 1 over r. So that means that the electrostatic forces drop off a lot faster as the atoms get further and further apart. So, for example, if so 2 molecules that are oppositely charged, if you just put them in vacuum, they will eventually come close together. But if you add this term, the electrostatic attraction will be much weaker, so it will simulate them being solvated in water, and they will come together eventually, but probably a lot slower. Another thing that is typically so I'll talk a little bit about the non-bonded forces right now, which are again the electrostatic forces and the van der Waals forces. So generally, what has to be done is, if you consider any single atom, like say this one over here. Well, okay, so first of all, the bonded forces are basically include just the atoms that are connected to it, and that's it. So it's usually the fastest step in the computation. But for non-bonded forces, you have to consider basically every other atom in the system. So and I didn't include all the atoms here, but basically just to give an idea, they could be atoms that are really far apart. So generally what's done is there is some cutoff radius outside of which those forces aren't considered. And because the forces drop off really fast, sometimes that's considered to be good enough for a lot of simulations. So that's a consideration to take into account when doing these simulations. Okay, so here's the basic molecular dynamics algorithm. So you specify how many steps you want to run it to, and I didn't say each time step is 1 femtosecond. So very small. So usually what happens is you can find the atom pairs. So that means all the non-bonded interactions. You have to make a list, basically an n-squared list. If you have n atoms, you can expect to have about n-squared atom pairs. But if you consider a cutoff, then what's usually done is only atom pairs with that cutoff, within that cutoff, are considered and included into that list. And that computation is pretty expensive, so it's sometimes only done every 10 steps. And atoms don't really move that much, so it's usually pretty accurate. And if you use a cutoff of, say, 15 angstroms, and then all the forces have dropped to almost 0 by 12 angstroms, then that's pretty accurate. So this is usually an optimization. It optimizes the simulation a little bit. The next step is to compute the bonded forces. So that includes the bonds, angles, dihedrals, and improper angles. And then compute the non-bonded forces. So that iterates over all the atom pairs. And then the integration is done to obtain the new atom positions. So here's running on the PlayStation. This is kind of roughly how, this is just running on the PPU alone. So finding the atom pairs, if I don't use a cutoff, I can just compute the atom pairs list once and then never do it again. So that's why I put here 0. But otherwise, generally, it takes a lot of time to compute the atom pairs because it involves getting the distances between every 2 atoms. And this is a system with, this is a pretty big system, maybe about 1,000 atoms. So that's why, these times are not really representative of smaller systems, but
what is BF?
BF is, so that's done using the brute force approach. So that means that you check every 2 atoms. And this is using a KD tree. So that breaks space up, and then you get then the checking the neighboring atoms is n log n, or it's actually a constant factor after you built the tree. Building the tree is n log n. So using that kind of an algorithm, you get much better improvement. So this is a scaling of increasing the system size by 2 in the number of atoms. So say going from 1,000 to 2,000 atoms. The time to using the brute force approach increases exponentially, whereas using a KD tree, it actually just about doubles. So that kind of shows that using a better algorithm sometimes for these things is probably much better than trying to parallelize it. Doing the bonded forces is, say, about 50 milliseconds. And with cutoff, it's the same time because it doesn't really affect this step. But then computing the non-bonded forces is actually the biggest chunk of time. So that takes about 1.4 seconds for this system. And then this is considering 1 million pairs. With a cutoff, there's less pairs to consider, but the time is still the dominant time, basically. So generally for molecular dynamics simulations, this is the dominant time factor. And that's what people really focus on, trying to speed things up. And then the integration is really fast, because it just loops over the atoms once. So there's basically 3 different parallelization approaches that I've come across in the literature. And one of them is referred to as force decomposition. So if you think of the a force operation being, say, a non-bonded force operation, where you consider 2 atoms and you compute the force, due to van der Waals and electrostatic forces. One easy way to split this up amongst, say, 6 processors is to just give each processor, say, n divided by 6 of these force operations. The force operation includes, so you have to send each processor both atom positions, and then some other properties of the atoms, such as the mass and, actually not the mass, but the charges and the minimum radius. And basically, once that computation is done, the processor just has to either store or return the force on both atoms, and it has to come back to sort of like the main processor where all the forces are added up, and then the integration is done. What I just described is sort of the approach I took, and it's sort of an easy approach to sort of think of if you couldn't store, say, every atom on every processor, because you just have to send each processor a certain number of these force computation units, and the processor does them and then returns the forces, and then you can just add up all the forces on every atom and do that. So basically, here's the algorithm, how it works roughly, and I'll just, so basically first set up the SPUs, send the control blocks with, say, the addresses where all these force operations will be stored. The bonded forces are computed on the PPU, just for simplicity for now. And then the computation for the non-bonded forces, basically all the non-bonded forces operations remaining are considered, and then they're split up into blocks. So each SPU sent a block with, say, a number of force operations. And in this case, it was 200. So the control block is sent to the SPU. The SPU is told to start processing. And then the PPU waits for each SPU to finish. And then once the SPU is finished, the forces are added to the two atoms that are involved in that first computation. And then this loop is done once all the SPUs are finished. And then it goes, and this repeats until there's non-bonded operations remaining. So for example, here, just to illustrate this, let's say these are all the non-bonded operations I have to do. And I'm going to use two SPUs. And each SPU can only store, say, 3 force operations. So each SPU is sent by a block. I mean that, say, these 3 operations are sent to each SPU. The SPU does them. The next block is sent to the next SPU at the same time, and then that SPU also does it. And this is iteration 0, for example. And this is done until all of the force computations are done. So here's the timing. So you might imagine that, as I said, there's a lot of communication overhead over here. So here's how this performs. So on the PPU, the whole the MD simulation per time step runs in 310 milliseconds. On one SPU, the time goes up to 630 milliseconds. So there's a lot of communication overhead here. On 2 SPUs, it goes back down to 390, and as the number of SPUs is increased, it gets lower and lower, but it's not that much better than really running it sequentially. And the reason is that the way I implemented it is it's pretty rough. One of the limitations is that, I mean, one very obvious optimization that should be done is that the SPU basically waits for this whole block to arrive and then starts computation. But really what I should have done is once one force computation arrives, you can already do that computation, and then instead of waiting for all of them to be transferred and then starting to do the operation. So I think that could have been a lot better.
Any double buffering?
No.
Double buffering.
No. So right. So this is sort of the simplest approach to, the sort of a simple approach to implement on this architecture, and it sort of scales well as the system grows. So if you can't store every atom, for example, in every SPU, this doesn't really care. The system can grow as large as you want. There's some other approaches that are done sort of in the literature. I didn't implement these, but another one is called atomic decomposition. So here, if you have, say, a number of atoms, you send each one of these atoms to one SPU, and then that SPU is solely responsible for computing the forces on it and also integrating to get the new positions. And then all you have to communicate is the atomic positions. But this is a little bit more complicated, because then you also have to have, every SPU has to know about all of the force computations that you want to do. So for example, in this case, it's just a non-bonded, but all the other force, the SPU also has to know about.
So that would be like the same example that we did in the executions?
Yeah, it would be. The only problem with that approach is that if the system was much larger than the SPU could store, then you couldn't store every single atom on the SPU, then an operation might refer to atoms that are not there. So yeah, it would be similar to that, but it would get more complicated in this case as the system grew, because you'd have to keep track of where each atom is and then implement communication if you don't have a certain atom to get that atom position and use it in the force computation. So yeah, this approach, okay, I'll talk a little bit more about this. This is,
You complete the BPU as one remaining, not SPU, but processing unit and store the remaining items.
That's true, yeah. So you only sort of give a certain number of atoms to every SPU, and then, yeah, that's true. And then you would have to sort of store every single force that that atom is included in on the SPU. Yeah. Yeah. The only when this would become a problem is say the system was much larger than you had local store. Then say you had like a tenth of the system on SPUs and then 9/10 of the system on the PPU. There wouldn't be it would be hard to sort of think of a scaling properly so a special case of this atomic decomposition is actually spatial decomposition. Okay, I'm almost done. So a special case is spatial decomposition, where what makes this approach sort of not good, and it sort of involves a lot of communication, is just this fact that some of these force computations or force operations that you have could include atoms on different units. So if you don't split up these atoms sort of smartly, then you could end up with a lot of having to communicate a lot while computing these forces. So spatial decomposition tries to address this, and basically you store atoms that are close to each other. So say I had this system and I wanted to split this up into on 6 SPUs, then I would give each SPU, say, a certain area of space. But you could see right away what the problem with this is that it's not load balanced. So some SPUs could not have too much work to do. And there's still some communication, because you have to communicate between neighboring SPUs, say, in some certain cases. But the communication is still probably a lot better than in the previous case, just for atomic decomposition. So here's the state of the art on this on parallelization MD, and it's implemented in this program called NAMD, and which stands for not another molecular dynamics simulator. So this initially NAMD 1.0 used solely a spatial decomposition, and they try to address this load balancing by actually creating many more patches than you have processors, and then you just sort of split these patches up, load balance them amongst the different processors. That didn't really work, so NAMD 1 didn't parallelize very well. So what they added later was they added this idea of patch objects and also compute objects. So basically, a patch object puts a number of patches in a processor, but then you can also create compute patches, which include all of these force operations. And these force operations are also equally distributed amongst processors. And then there's a lot of communication between these two. And it started off with sort of a message-oriented communication. Then it moved to a dependency-oriented communication. So that each compute object would sort of signal which atoms it needs. And it also sort of optimized things by doing communication and force computation at the same time. So it did that really well. And actually, it has really good parallel performance. So here, on this graph, it shows the number of processors times the time per time step. And as the number of processors is increased, optimal parallel performance would be a straight horizontal line, which is pretty close to what they achieve. And they also did it on many thousands of processors on Blue Gene. But as you might expect, the more processors you add, the step time actually still sort of levels off at a certain time. So I guess I'll skip the sort of live demo I was going to do, but I'll just show one more thing. So here's sort of the kind of systems that I was looking at. This is actually a simulation that was done on one of the PPUs and then recorded in a positions file. And there's 5 different molecules here. I'll make them. So here, generally what happens is first they're just placed randomly, then they're unoverlapped just very coarsely to make sure that they don't, huge forces aren't added into the system. And I'll just color each one differently. So here's what happens during the simulation. And here, in this simulation actually, the positions were recorded every 20 time steps. So that's why it sort of seems to go a lot faster. If I did it on a single molecule, and I should have done that first. So here's what a single molecule of this looks like. And this is a protein with 8 residues, which is pretty big. And this is running in real time on my computer right now. So a small protein, like on a small system like this, it runs reasonably fast. But as you add more and more of these things, the computations do get pretty expensive. So parallelization really helps.
Great. Any questions? All right.